it. Okay.
Yeah.
So I hope. Okay, so there is this. Okay, I see. Yeah. Excuse me also for the wrong date. I took the same seminar as I did on SISSA. So the title is the folded XXZ model overview and open questions. Now these open questions, there will be fewer than 2 weeks ago because there was some preprint recently in archive that made some steps in solving some of them. But anyway, I'm going to do this nice story overview of what I did when I was working with these guys in Paris-Saclay in the period 20 to 22. So in particular, the collaborators, the main collaborator Maurizio Fagoti, and then Kemal Biggio and the PhD student Saverio Buccini. So what's this story? What is this folded in the folded XXZ model anyway? So this will be approximately the outline of talk. I will make, before doing the motivation, I will actually introduce the so-called folded picture. And then I will do, I will go to a bunch of topics that have a bit to do also with integrability, which is my background. But I will try to not do so much with integrability. I will just show the essential ingredients which are necessary to understand some things like Hilbert space fragmentation, the eigenstates of the model, the thermalization, relaxation, and this kind of stuff, which is maybe more suitable to the community here. Anyway, so what I'm going to talk about is the following. So we have basically considered, and I will later in the next slide, I will show why we consider this, why we're interested in these kind of questions. Families of models that can be written in this kind of way. So there is some Hamiltonian, which has some parameter, a coupling constant, that basically links to a term that has equidistant spectrum. So for example, this could be any kind of combination of Pauli Z matrices, like Ising term or ZZ or anything that has a spectrum which is equally distant, so the energies are equally spaced. And this term here should basically satisfy the following algebraic properties. So it should commute with this term HF, and then it should satisfy this kind of precession equation with this operator F, and also with F dagger similar. Okay, and in this kind of families of these models, you can play a very nice game when this delta with this coupling parameter is large, and you can play the strong coupling expansion. A particular version of it that was basically also inspiration for us was the McDonald, Gerwin, and Yoshioka expansion in the large coupling of the Hubbard model. But so what does this folded mean here? Where does it come from? And what's the point of all this? So what we want to do is the following. We want to consider what happens to the spectrum of the model and the model itself when delta is large. Okay? So if I have finite size system, then the spectrum when delta is large enough will look like bands which are separated by delta. Okay? And because of this algebraic relation here, the bands, so the states, which will be delta apart or an integer multiple of delta apart in the spectrum, will be connected by the action of these operators F and F dagger. One will go up, one will go down. And the idea of the strong coupling expansion, which is actually something old, this is not really a new idea, is that when I have a very large delta, these transitions between these bands become prohibited, essentially. So in the leading order of this large coupling expansion, I can just cut away these terms that cause transitions between the different bands. And then the model is essentially only the terms that are HF and HI, which has equally spaced spectrum. Yeah? And basically, that means that this HF is essentially has the same spectrum as the original model at large delta, modulo integer multiples of delta. So it's basically the spectrum of original model kind of folded together. So the number of states in the initial model is 2 to the L, where L is system size. And I'm considering, for example, spin 1/2 chains. And in the new model, I again have 12 states, but they're basically completely, the states are completely closely packed in the energy, on the energy scale. So there are a lot of emergent degeneracies going on here, which implies that I should have a lot of emergent symmetries. Yeah. Now, of course, this picture is limited to finite size effects, because when I have thermodynamic limit, there will be no bands because the energy scales with L. So I will have these states will be all over the place on the energy scale, but still the essential idea of cutting away F will still hold, because F will still cause transitions between states that are delta apart, and delta is very large. Okay, so this picture exactly here will be a bit different, but the main conclusion that HF has the same spectrum as the original model, modulo integer and integer times delta, this will still remain the same. So this fact will remain. So this HF I call the folded model. And my point is the following. So why I would be interested in this, I want to consider relaxation in quantum models, in spin chains. And in particular, I want to consider the non-trivial part of the dynamics at short times on some particular scale, which is governed by this coupling parameter. And what I will do in this, in what I call a folded picture, I will apply the trivial evolution, which is highly oscillatory with periods proportional to 1 over delta, and is generated by this HI, by this operator with equally distant spectrum. I want to apply this to operators. And then what I want to do with states, to gently evolve them with this non-trivial part, HF. Okay? And I can get very interesting dynamics generated by this HF, by this folded model. So, okay, this I will skip, but the motivation, for example, I could consider perturbations of XXZ model, for example. I just put here XXZ because I will use it later. So the title of the talk is folded XXZ model. So I will do this procedure at the end in the XXZ model. So this is a spin chain. I will be more exact what I mean by this sigma. These are Pauli matrices. Then I can consider multiple parameters here, which can also be large. So this picture can be actually generalized much more. I can also consider, of course, other models, and I can do this folded procedure. I can get this HF model. So this folded model, which has rich emergent symmetry structure. I will mention it later. And I consider time evolution. And what I see is basically that if I smartly choose observables, and this is basically what some members of this community here that are present today are sometimes doing. So we basically are doing the time average of correlation functions up to a particular time. And this at long times, at large times, should go to a diagonal ensemble prediction by the eigensymptomalization hypothesis. So these curves should all at long times reach this prediction, the diagonal ensemble prediction. But at short times, one can observe if these correlators Cj are smartly chosen, one can observe plateaus whose longevity basically scales linearly with delta, this delta. So this is log scale in time, for example, and here you see that I'm basically considering decades of delta. So each time I multiply delta by 10, these plateaus will basically increase with longevity, and this orange curve above is the folded model. So the first order expansion in 1 over delta of one of these models, for example. And when I consider higher order terms, which I can also do, so the expansion will be valid up to longer times. Okay? So there is this nice theory about these time scales up to which the perturbation theory is sufficient to describe the dynamics of the original model, which was put out in a bit different setting in Floquet models by Dimabani and Derek Hoch-Beniers. 17, but essentially the point is the following. So we in our community were interested in relaxation, yeah, and of course up to now typically people have been considering in integrability what happens at very large times, but not a lot has been done. There have been some works, of course, but not a lot about what happens on intermediate or short time scales. And of course the plateaus here clearly should be governed by the symmetry structure of the model that basically generates evolution on these time scales. And if the symmetry structure, of course, is different than that of the original full model, then there should be a plateau. So for example, the generalized Gibbs ensemble prediction or diagonal ensemble prediction will be different than that of the original model. I will get into details in later slides, okay? So what happens if I do this in the XXZ model? So I have a spin chain, sigma alpha Pauli matrices. Yeah, so each local filter space is is a linear superposition of spin up and spin down. And this is basically the model that I get. So there is some hopping term, nearest neighbor hopping term, which is basically constrained with outer spins. If you look at the pictures that basically tell us the hopping process that can occur in this model are the following. So I have two spins in the middle which can exchange provided that the outer two spins are co-aligned. Okay, this is basically essentially a feature of this model, which means that if I have a domain and I have a single magnum, a single flip spin, this spin can propagate. Okay? And an interesting feature is that when this spin, for example, here in this case, it's not clearly seen, but I have a spin up that propagates in a domain of spins down, and then suddenly it hits a domain of spins up. What happens is that it changes its orientation and propagates through the opposite domain, as the opposite spin, basically. And then it exits this domain and is again with the same orientation as before entering the domain. But the domain itself has shifted. So there is kind of interesting dynamics, the constraint dynamics that is generated by this model. And what one can see quickly is that because of this kind of allowed hopping processes, there are emergent symmetries which were not present in the original XXZ model. For example, XXZ model had, of course, magnetization, which is conserved, but there are additional symmetries like domain wall conservation, which now arise in its large delta limit, so in large coupling expansion. And then there are, of course, a bunch of Z2 symmetries like spin flips in various directions. And it turns out that this model is integrable, which is what was basically the main part of our work, so how to solve it. And this fact that it's integrable is apparent in the fact that you have like extensive in the system size of conservation laws which are local. This means they are translationally invariant sums. So this sum goes over J, which is a lattice site of some local terms Qj, which are localized around J. They act on a few sites around this index J. Now, so what we wanted to do with this model, of course, is to consider whether we can solve it. Okay, I think its solution was the main issue that we're considering. And now in integrability, how you solve a model. To solve a model, you have to, of course, means that you have to get the eigenstates of the model. So you should get the eigenstates, and to get the eigenstates, the procedure is typically first to identify some kind of particles that you can put on top of a vacuum on different positions, and then you take combinations of these kind of states and fix the combination in such a way that you get an eigenstate. And to identify these particles which behave well, and by behave well, I want them to scatter elastically and otherwise propagate freely. To do that, I want basically, I have to have a local density of the Hamiltonian, which is simple enough. And it's easier to do this if this local density acts on a small amount of neighboring sites. For example, when Orbach solved the XXZ model in 56, he used magnons, so single spin flips. This was a similar solution to what Bethe did in 20s. But the point is that it was kind of, let's say, he could simply recognize these particles because the local density was two-side density. It was basically hopping on two sides, and there was some additional potential energy term. But in this case, we have a four-side Hamiltonian, so it's a bit more difficult to identify what are the quasi-particles. So what we did first was to reduce the local density of this Hamiltonian by the so-called duality transformation. Yeah. So there exists a family of duality transformations, one of them being the Kramers-Vanier duality, by means of which Kramers-Vanier showed the Ising transition. It's also called bond-side transformation, and it looks like this. So what I will do is I will map, so perhaps this one is the easiest to consider. So I will map the co-alignment or alignment of nearest neighbor spins into a spin variable on the bond. So if I have two spins that are co-aligned on the original lattice, then on the bond between I will have a spin up. Instead, if I have oppositely aligned spin, I will have a spin down on the bond between them. So what happens to these objects that I identify? So the folded model So is this 4-point Hamiltonian, and here below I have some of its symmetries, the simple U1 symmetries. Magnetization, then staggered. So this should be staggered. Here should be sigma zj plus 1. Doesn't matter. But I have a domain wall also conservation. I can forget this staggered one. Let's consider this one and this one. Well, of course, this one will just become magnetization because of my bond side transformation. But interestingly, the magnetization of the original model is mapped into something that is essentially a non-local object, a sum over Jordan-Wigner strings starting at different points in space. And the model becomes a three-side Hamiltonian, which is next nearest neighbor hopping, constrained by the spin in between. So basically, a spin can jump for two sides if in the middle side there is a spin down. Okay. So is there something I can write with? So there is this dynamical rule here. Oh, yeah. Okay. The only dynamical rule is the following. So this can happen. Yeah. So if I have two spins down, for example, they can exchange with spin up. So this is the model that we based where we can easily identify the particles, which I will use later to show nice properties of the model. Like it will be clear how these symmetries emerge, and also the fragmentation will be, the emergent fragmentation of this model will be kind of clarified. So how does this proceed? Yeah. So this is the dual folded XXZ model in the dual picture. Yeah. So as I said, so two particles. So yeah, if I have a spin up close to two particles which are spin down, then they can exchange. And it turns out it's very convenient if I split my lattice by joining adjacent spin sides. So any pair of spins, I will join them together. So 1, 2, 3, 4, 5, 6, etc. And then on these macro sides, so by macro side I mean a pair of neighboring sides, I will define particles which are represented like this. If I have a spin up, this will mean I have one particle. And if its position is odd, it will be of type 1, because 1 is the parity of the position of spin, it's odd. And if it will be on odd side, it will be type 0, because it's, sorry, if it will be on even side, so on the second side here, it will be type 0, because parity of even position is 0. And this one will be orange one, and the odd one, the type 1, will be green one with lower triangle. What can happen is that two particles of different types, 1 and 0, can hop on the same macro side. So this is this above. These are just two particles on the same macro side. So it's 1 followed by 0. And then if I have nothing, just two spins down, this is vacuum for me. Excuse me. So let's consider the dynamics. How do these particles move? So first, let's consider these two particles here. So these two red spins, I hope the red can be seen, probably not really, but these two red spins simply cannot jump. And this is because I have XX mole on next nearest sides. And that means I have naturally a Pauli exclusion principle. Exclusion, not whatever. More interesting, okay, so then I can consider these two spins. You see, this one can, what happened is, so this spin up can jump for two sides, of course, now, but it will get stuck because it will hit the other particle. Okay, so this is not really so much interesting. Then it can bounce back. This is just free bounce off. It's similar to what happens in XX model. Then let's consider this one, for example. Here, I have a kinetic constraint which is not satisfied because the spin between the positions where I want particles to exchange is up. You see, but I want it down because I have this projector. So here nothing can happen again. Now more interesting is this. Yeah? So this is the one that I showed here. These two particles can hop together basically, and they can hop on the same lattice macro side. Yeah? And when they do this, since you have particles that are basically two particles that are on the same effective lattice side or macro side, you will get a non-trivial scattering phase here. Yeah? And for those of you who are interested in integrability, it turns out that this scattering phase is very simple. And this scattering phase is important for integrability.
which I will tell you in the next slide why. This is probably the simplest scattering phase that you can get in integrable models. This will also hopefully be clear in the next slide when I present how this works, because it's exponential in momenta, and it allows the beta equations, the equations that need to be satisfied for the ansatz to work, to be linearized and then solved. So, yeah, so how do I do this now? So we have now identified these particles by means of which I can construct and diagonalize the model. And one thing in beta ansatz is that these particles should scatter elastically, which I will claim later and argue is that this is basically that this follows from the fact that you have an extensive number of these local conservation laws. And this allows you to clearly define the momenta of these particles. What's going on? Okay, here, yeah. So, and the elastic scattering means that these momenta of particles are simply permuted, okay? But then in our model, we have an interesting situation of having different species of particles, and their sequence is conserved. Namely, in any of these cases, you can see that the sequence of orange and green triangles has basically, apart from moving around, their sequence is basically conserved during this scattering process. They cannot jump across one another. Okay. So basically, in this language of particle types ones and zeros, this means that the binary sequence of ones and zeros, which tells me how the particles are put into the lattice, is conserved. So basically, each eigenstate will have two quantum numbers. One will be the momentum of all the particles, and the other one will be this binary sequence that tells me what is their species configuration, the initial state. And now what one does in beta ansatz, how one solves the model is, well, one considers what happens when I move. Okay, so now we get particles, but what we are actually interested is we would like to follow what happens to momentum when I scatter these particles. So momentum simply translates from one particle to another. The momenta with each scattering are just exchanged because this is elastic scattering. So I can define another set of quasi-particles, let's say, that are called tracers and that follow the momentum. And this tracer, basically, what will happen, what I should do is I should consider what happens when this tracer comes around the spin chain. So with periodic boundary conditions. So first of all, it scatters with other particles. Momenta get exchanged, but the momentum always hops onto the next particle. So it comes to the other side. And basically, because periodic boundary conditions, it is back on in the initial position at the end of the day. So the wave function after scattering, coming back to initial position, should be the same as initial wave function, which tells me that the phase acquired should be equal to 1, yeah, because otherwise wave function is not well defined. Now, the scattering phases give one contribution, and the other contribution is simply because this quasi-particle has traversed the entire chain. And this is basically the typical thing that people do with beta ansatz. This is actually beta ansatz equations. So the thing that you have to do, you have to identify this scattering process. Okay. Once you have this scattering matrices, you can do magic, let's say, although this is a bit overreaching, but yeah. And you see now what's so interesting about our scattering matrices. You remember, if you recall, it was exponential of difference of momenta. You see that in this case, everything will be basically linear in momenta. So I can just take logarithm and I can solve them. Everything is linearized. So this is why this is called the simplest beta ansatz equations. So people call integral model solvable, but they like to forget that at the end of the day, you typically have non-linear equation, non-linear set of equations to solve. In this case, it is not so, okay? In this case, you really can get analytically the solution to these beta equations. And now, in our case, because of specifics of this model, please tell me when I have, how much time I have later. Thanks. Here we have an interesting, peculiar situation. In Heisenberg model, for example, all you need is this quantum number which tells you the momentum of particles, but here you also need this configuration of degrees of freedom somehow to kind of characterize the configuration of degrees of freedom. And if this B, this if this particle sequence is just random binary sequence, okay, with no order or no symmetries, then these are the data equations. So I have total momentum, which should satisfy a similar equation as in free particles models, but with L half. So the effective system size, remember, we are pairing 2 and 2 sides, that's why I have L half. And then there is additional equation, which tells me, which basically constrains any two momenta of particles and has another parameter m. And this m counts the number of occurrences in the configuration where the lower triangle, this particle, so spin up on odd side, is followed by a particle represented by spin up on even sides. This is exactly the subconfiguration which can lead to two particles being on the same macro site. And in that case, the effective size of the system increases because one macro site has been released, because two particles join onto the same macro site. That's why you have this kind of effective system size L half plus m. Each time two particles can jump on the macro site, one macro site is released and is basically effectively a bigger system. Now, the counterexample of this B has no symmetries would be a symmetric B, which has basically a unit cell. So this would be like 0, 1, 1, 0, 1, 1, which repeats itself. And in that case, you have, this becomes a bit more complicated, but it can be done, and it's still linear, so you can still solve it. Okay. So I would just like to present a bit first the general overview of how beta ansatz in general work, because it's a nice model, and I think you can easily get some ideas how this beta ansatz works in general. So you can solve because it's linear, and what you get is, so the first term here is basically just 2 pi times some quantum number. Let's call it, let's say that this is an integer. This is the same as free models, but there is an effective system size because two particles can hop on the same macro site. But then there is additional term, which is essentially proportional to the total momentum of the system. Yeah? So it's a sum over these quantum numbers, which I would also recover if I would sum over all momenta, essentially. So this is kind of proportional to total momentum P of the system. And this is where interaction hides. So if people ask you, how would you characterize interaction in an integral model, for example, it means the following. If I want to specify a state, I have a vacuum, I put in particles. So I basically choose which quantum numbers are occupied. In free models, that's it. I remove one of them, nothing drastic happens. I can put another one, the rest remain where they are. But in interacting models, there is interaction between particles. So when I plug in or change one of the quantum numbers, all of them will kind of shift and change. They feel each other. So this feedback that happens on the level of momenta, for example, so when I add or remove a particle to a state, the momenta of the rest will be affected. This is the essence of interaction, okay? And it's clearly seen and characterized in integrable models. Now, let me grasp this opportunity just to give you another, let's say, lesson in how integrability, how people perceive integrability in two different ways, which are essentially the same. So some people say integrability means solvability. I can solve them all. I can give you eigenstates and eigenenergies. Other people say, yeah, integrability is just, you have infinite number of local conservation laws. And this is essentially the same. Why? Clearly in this model, what you can see is that if you compute the eigenvalues of the conserved charges that I was mentioning, the ones that are translationally invariant sums of local densities, then you see that the single particle expectation values are just trigonometric functions, basically a basis of trigonometric functions in the momentum, okay? And because of they are the basis, I can recover the momenta if I give you all expectation values of these charges. Yeah? So basically, the fact that you have extensively many charges which are local tells you that you can recover and fix momenta of these particles, which will then just permute between themselves because of elastic collisions. So that means that basically the solvability and existence of these local conservation laws is essentially the same thing. Okay, now we come to first open question, which I have to comment a bit and change because it's not completely open anymore, but okay. So the standard translation invariant charges, which you can find in all models. So these translation local invariant charges are in all integrable models, in standard ones. Via these conservation laws, you can construct the momenta. You can reconstruct the momenta. So the particle, so the momentum configuration of the eigenstate. But we have another quantum number, which is the species of particles, the sequence of particle species. And the question is, how do you construct that? And clearly, this should not be linked to local conserved charges, because you can pack any amount of particles in the system, like extensively many in system size. It can scale with system size, and this still gives you a quantum number, which is basically, which has L numbers inside, if you want. So one of these, for example, one of these charges we have identified already in the original papers is the M that counts exactly the number of particles, of green particles followed by red ones. And it turns out that this is kind of a bit unusual object in a sense that, so it's a translation invariant sum, but it's a double sum. So one sum is over lattice side where this operator here in the interior is located, but there is another sum which basically goes over the range, over all possible ranges of this internal operator. These kind of objects are not really local, but still have extensive properties, it turns out, and they're called quasi-local. And the question, like, is what are the other missing objects of this kind? Possibly completely non-local, so even not in this kind of, not written in this kind of way. So they could be completely non-local objects, not even a sum, but just one block of some Pauli matrices that completely characterize this P. Remember, this M only gave me one property of the configurational quantum number B, namely the number of greens followed by yellow ones, by red ones. And it turns out that this is strongly linked to Hilbert space fragmentation. And in a few slides, I think probably 2 or something, I should describe how this works in this model. So once you have this kind of charges, you can basically play, they basically cause fragmentation of Hilbert space into exponentially or polynomially many, depends on what kind of fragmentation you have, kinematically or kinetically constrained and closed subspaces. Now, I mentioned that this open questions is a bit, since 2 weeks, is a bit obsolete because there has been a paper which basically, so recently, just like 1 week ago, so this Hungarian group, which actually essentially worked a bit later on the same model, like a lot, they produce a lot of papers on different aspects of this model also. They basically provided a partial answer to this, so how you can reconstruct these configurations, and it's basically hidden in a kind of symmetries that are called matrix product symmetries. So these are basically operators that have very nice, very low entanglement operator entanglement entropy and can be written in terms of tensor networks, nice tensor networks. Not so nice though, because the bond dimension of this network is kind of 8 or 7 sides, so it's kind of obscure. So they used very interesting tricks to basically provide the solution. So basically they identified some of the symmetries that give you these configurations.
Are you going to explain more? Or?
Yeah, please ask, otherwise.
No,
Yeah.
okay. I didn't really understand this last point. So
okay, so the point was, the open question was, what are these? The first open question was, which is now solved. Let's say, yeah.
Yeah, no, that's clear to me. I didn't understand this matrix product.
Yeah. Thanks for the question. So what he does is basically he writes the answers for these kind of operators. Similarly to what you do with transfer matrices in integral models. You have auxiliary, so you will have objects which are basically tensors,
yes,
that have 2 legs. Okay, 4, but this is operator, so it has one input.
Auxiliary space.
Yes, you have auxiliary space, exactly.
Yes.
This is some auxiliary space. And this is then a quantum space where you have spin. So here you have spin.
Okay.
Then you put these objects together.
Right.
And then you trace over the auxiliary space. And this is your, so yes. So similar stuff you do in integrable models to construct standard local conservation laws, but they depend on some spectral parameters which are connected to momenta. Instead here you can use this kind of structure.
There is no spectral parameter.
Yes, there is no spectral parameter here.
Okay.
And then you demand that this commutes either with the local density of the Hamiltonian. So the Hamiltonian is a sum of some local terms, or the full Hamiltonian, depends what you want. And you can get actually symmetries of both kinds. And one class of these symmetries is related to these configurations. But the point is that this auxiliary space dimension is quite large. So it's not non-trivial to find this in the original model. You have to do some kind of additional duality transformations on top of the one the used by Kramers-Vanier that I used. So anyway, okay, maybe this is not really. Maybe we should go to fragmentation now. So I would just like to mention that there is still an open question related to this. Namely, so people are actually not interested in our community, not so much interested when you in the finite L basically, but they want to take typically large L. And in that case, you have what is called thermodynamic beta ansatz, so you can do thermodynamics in the model. And basically what happens to the state on the level of the state, you don't need all the details of momenta and these particle configurations. Instead, what you need distribution of momenta in the momentum space, is the so-called root density. And then you need some details about configuration on some chosen scale. So you have to do some coarse graining. And of course, the question is, what is the coarse graining? But in this raw picture, it's basically what people typically do. So you have this momenta, yeah? And when you increase L, there is more and more of this momenta, and it's basically convenient to define their density. And you have some cells where you pack this momenta, and the value in each cell will basically be the value of this density. But you can reconfigure momenta inside the cell, and this generates entropy basically, because you have many different reconfigurations which give you the same macro state, right? So this is basically what you get, and this is the famous Yang-Yang factor in the thermodynamic beta ansatz, which counts in how many ways you can reconfigure momentum. And this factor, logarithm of this term, of just this term, which is product over momenta, is this configuration, so particle configurational entropy that is also there in every integral model, like in X, X, Z, X, X. In our case, we have additional thing. We have also this B number. So I have additional degeneracies, which come from these degrees of freedom that describe what are the species of particles. And as I will show next, it's basically related to fermentation. And the open question here is the following. So now we have been considering this stuff only with this M quantum number, the only quantum number that seemed relevant for us. But now we have access to higher of these charges. So can we do, so what kind of, can we add this to the parameters which specify my thermodynamic state? This is the question basically. Because why this is useful? Because once you have thermodynamics, you can also consider, for example, inhomogeneous states and their time evolution in large systems. And so basically what you do is you promote these parameters that specify macro state to space and time dependent objects. And then you prepare some inhomogeneous initial state, you evolve it with time, and on large scales, you can get the so-called generalized hydrodynamic description. And the question would now be, what happens if I have these additional parameters? So how many more details about the local configuration of state can I basically involve to get something non-trivial in the hydrodynamics? But for this community, probably this is not so relevant. I would like to go really to Hilbert space fragmentation now. So if you will excuse me, I will just not go into details about this hydrodynamics. So let's see what is about this Hilbert space fragmentation in our case, and where does it come from and what does it mean anyway. So remember that we had this model HF, yes, which was 4-side Hamiltonian, and we used Kramers-Vanier to map it into a 3-side Hamiltonian. And this Kramers-Vanier involved this bond-side transformation. So if I had in the original model 2 aligned spins, I would get spin up. If I had oppositely aligned spins, I would get spin down. So how does this translate in our picture? Suppose that that I have in the original model a domain wall. Then this domain wall basically is a sequence of aligned spins, which is in the dual pictures spins up.
Then the domain wall is oppositely aligned. So because of this bond side transformation, it will spin down. And then I have again a sequence of spins down, which are aligned. So I have again spins up in the dual picture. So I have the following correspondence: a domain wall, which is called a quark in the community of Hilbert space fragmentation that's dealt also with this particular model, will be mapped basically into isolated spins down. And this is immovable because you see in the dual picture, this is clear because the isolated spin is not of this type. So isolated spins cannot move and jump. Only if I have two spins down, they can jump around. So these are immovables. Then if I have two domain walls that are nearest neighbors, so bound domain walls, in the community of fragmentation, typically they call them mesons. And now this corresponds, you see, two domain walls. So I will have two next nearest spins down in the dual picture. And this can move because the rule can be applied here. Yeah? So the mesons are movable and the quarks are immovable. And the emergent symmetries basically just tells you that basically when mesons move, the domain wall number is conserved. But on the other side, there is additional thing. Quarks cannot move because if they would move, one domain would become larger, the other one smaller, which would necessarily mean a bias between number of spins up and down. And that would mean that the conservation law of magnetization of the numbers of spins up minus down would be violated. This is conservation laws, this cannot be violated, therefore quarks cannot move. Now what I will do, how do I get these fragments of Hilbert space? What I do is the following. I join two states. In one state, where is the cursor? Okay. In one state, in the original picture of HF, not HF tilde, but HF, so the upper one, I will join domains which have more than two co-aligned spins. And these are unbound quarks. They are immovables. So the domain walls here are more than one side apart. So in the dual picture, this will mean I have I have isolated spins down. They are not close together. So this will be a jammed configuration. Nothing will be able to move. Now I join this state to a state of closely packed mesons. So a nil or anti-nil state. You see the domain walls are closely packed now. And in the dual picture, that means that spins down will be closely packed. So I'll have a vacuum of spins down. I join the state. And now I apply Hamiltonian density, for example. And what I get is that these unbound quarks will suddenly, in the original picture, the closely packed mesons will start propagating into the sea of quarks. But in the dual picture, it's a nice representation. The particles that are initially jammed and are basically labeled by this B, by the sequence of their species, which is a binary sequence of ones and zero, they will start propagating into vacuum. But this sequence, this is a good quantum number. It will be conserved. So irrespective of how I expand this gas of particles, they will still be associated with the same sequence. And this sequence basically labels a part of the Hilbert space where the dynamics of this gas will be constrained to. And since I have exponentially many such configurations, binary sequences, I will have exponentially many different kinetically closed subspaces of Hilbert space, which will then have to be polynomially large, and that is called strong fragmentation. So in proportion, all these subspaces are kind of equally sized in the large size limit. None of them prevails, okay? Yes.
So what you're doing here is a bipartitioning process. So you have half of the system in the state.
But it's not half. It can be any size. That's additional thing. Yeah. So you can have any size.
And then you put the rest some sort of.
Yes.
So,
yes.
Okay.
And the dynamics then will be constrained in one of these subspaces.
And what is the advantage of looking at the same thing in the dual and original picture?
In the dual picture, it's much easier to identify the particles and play with them. So we solved them all in the dual picture because we could do beta ansatz. In the original model, the beta ansatz particles would be something like domain walls. And but this is clear.
a posteriori, I mean, it was not, it couldn't be clear completely.
Okay, but if now, so now a posteriori, I can forget about the goal picture completely. And
It's still kind of complicated. I mean, yeah, in principle you could, but it's, I mean, it's not much nicer, I think, to think of this of these particles in a vacuum, which is natural, than domain walls and mesons and quarks.
Okay.
And now with this fragmentation, there is another question that is linked. How much time do I have, by the way, because we were late? So we should. Okay, we don't have. We can't. Yeah.
no, I mean, in principle, you have still.
There is a class after.
Yeah, I think
Probably. Yeah. So let's.
Have to leave sharp,
Yeah.
sharp.
Yeah.
Yes. Yeah, okay.
But
So
there still are like 10 minutes.
yes. How much do you give me of these 10 minutes?
Wrap up. So that
Okay. Okay. Fine. So typically, when you have fragment, well, not. Yeah. Okay. Let's say typically, although this is to be argued, but when you have fragmentation, you sometimes, let's say, sometimes have also the quantum scars. So these are basically
Special low entangled states which are equidistant in energy. What's going on? And equidistant in energy, but they're in the middle of the spectrum. So basically, you can have
states that are basically equidistant in energy everywhere in the spectrum, and they are low entangled. And you can have operators that connect them, and these operators
people sometimes called dynamical symmetries. So basically, they don't commute really with Hamiltonian, but satisfy this kind of equation. So you see that
they go from one state to another, and these two states are
for some fixed number apart. Okay, so this is basically this separation between these states. And if in certain models, like in constrained models, typically like PXP model that was considered in the original paper, you have this kind of states that have basically this that are equidistant. They have separation, which is fixed, and then you can prepare initial states
that basically have overlap with all of these kind of states in the middle of the spectrum.
And this causes coherences in certain correlation functions that do not disappear when you go to large L and large time limit,
Which kind of shows up as oscillations in the correlation functions. And if you see oscillations in the model, typically it signals something with either quantum scars or dynamical symmetries. And these dynamical symmetries are not only kind of more general. So if you have just like one ladder of these states in a generic system which is thermalizing, then these are called scars. But you can have models where basically you can have operators that basically translate between any selection of this kind of state. So you can choose any state, and then you will construct a ladder using this symmetry. So these are really kind of on the level of global symmetries of the model. They are not only in part of the Hilbert space.
And a particular model is XXZ in the regime where delta is smaller than 1. You can consider this kind of symmetries basically satisfy when you turn on magnetic field, this kind of nice equation, which tells you that if I solve it, so Y will basically be proportional to itself, but it will have a oscillating factor when I time evolve it. And you can have basically certain correlation functions, like you can take sigma x expectation value. It will have overlap with this quantity, and it will have persistent oscillations in a thermal state if you wish. So you can put any thermal state, even generalized given sample, and you will observe this kind of oscillations. So, and this is what actually was observed by a Hungarian group, and this kind of oscillations actually should be linked with kind of some symmetries that we expect actually to be hidden, similarly to what happens in the XXZ model in the integrable structure itself. Okay, so this is because I don't have time, but just a quick. And then there is another interesting thing that we considered, and I should mention probably, and then I will just stop. So jammed states of the model. So consider now that I have these particles that I closely packed. So there are just isolated spins down. And in the picture of this of triangles, this would mean that I have them closely packed, which means I have jamming. Nothing can move. Yeah, and basically, this kind of mimics something that is well known in Rydberg atoms. So these are atoms where you can excite
one or more electrons very far from the center to have very far principal number. And then by tuning the distance between them, you can prevent two neighboring atoms to be simultaneously excited. So that would mean that basically I cannot have nearest neighbors that are spins down, where spin down would mean excited state. And this is basically, in this case, the Hilbert space of such states grows like a golden ratio to the system size. This is called Fibonacci sector, is well known in the Rydberg atom blockade models. And what is interesting in this dual folded or folded model is what happens if you unjam locally this kind of configuration. So you turn one of the spins down in order to get two spins down somewhere in the system. And it turns out that with time, the spin profile will completely collapse basically on a macroscopic scale. And this will be stable on, for example, ballistic scale, or if I put integrability breaking perturbation on some diffusive scale, for example, and one can solve these kind of things in these models. I'm sorry, I don't have time for these details. Probably we should stop because of that.
How big is your system?
This is basically infinite system, let's say. Okay.
On the left.
So on the left, yeah. So the point is the following. So when you break locally the stuff, so there is something going on locally, and it spreads, and there is some kind of light velocity, light speed, for example, in lattice systems with shorter interactions, which tell you that you cannot get out of the light cone. So the system size effectively is infinite because out of the light cone nothing is happening. So I don't really care how big.
Even for the numerics.
Yes, for numerics you can do DMRG, you can do arbitrarily large, but it should be much larger than the times up to which you propagate times velocity. Okay, that's the only important stuff.
I didn't answer the law. So there are too many curves. I get it.
Yes.
So you have some initial spin configuration, which is
The initial spin configuration would be basically what is out of the light cone because.
yeah, there are two things out of that.
Yes.
Yeah, so which one? The one on top or?
No, this is the state. Up, up, down, up, up, down, up, up, down, up, up, down. This is sigma z.
Okay, no, oh, I know.
Initially, everything is like this, but then.
So they seem to overlap, but they don't, right? This point.
Yes, no. So basically, you have like discontinuous profile, but some of the spins, depending on the initial configuration around them, will be on one of the curves, and some will be just in the initials.
So if I join the lines, then I see a huge mess, but still.
Yes, it will be something like this,
right.
And there will be no transport because of this. Okay, the current will be simply zero in the large limit, but there will be macroscopic organization. So this is the interesting point. You have macroscopic spin reorganization, but no net current or any kind of local current inside. And this is so. The interesting point is also I break integrability. I just change the scale of the phenomenon, but it's still on big max. Yes. Diffuse. I think it's diffusive. Okay, there is some.
Right.
Okay, I should end here. I mean, so I just wanted to say that it's very interesting that you have these families of models that have been here for centuries and they have been solved and considered solved, but you can still come and find something new. I mean, this is really an amazing feature. That was essentially my point.
Thank you.
Thanks a lot.